Mars looks dry enough to be dead. But beneath that dusty, rust-colored surface, enormous quantities of water are frozen underground, and some of the deposits are so thick that radar can trace them for kilometers. One of the most remarkable examples lies near the Martian equator, in a region called the Medusae Fossae Formation. In 2024, researchers analyzing new radar data from ESA's Mars Express found evidence that parts of these deposits are made largely of layered water ice beneath hundreds of meters of dry material. The buried deposits can reach about 3.7 kilometers in thickness. Think about what that means. From orbit, Mars can look like an endless desert. But the desert may be sitting on top of a frozen archive. Not just water, climate history. Layer after layer of ice can preserve evidence of how Mars changed as its orbit and axial tilt shifted over enormous spans of time. So here's the mystery. How did all that water get there? Why was it buried instead of disappearing into space? And what can those frozen layers tell us about the Mars that existed billions of years ago? The strange part is that scientists didn't drill down and find this ice. They detected it without touching the ground. And the tool that revealed the secret is essentially a radar system orbiting another world. If that already sounds incredible, stay with this story, because the deeper scientists looked, the more complicated Mars became. And if you love discoveries that completely change how we see other worlds, follow the coded tales for more. For a long time, the simplest picture of Mars was easy to understand. A cold desert, a thin atmosphere, water mostly locked away as ice, with large deposits concentrated at the poles. And on the surface today, liquid water isn't stable for long under ordinary Martian conditions. Mars's atmosphere is extremely thin compared with Earth's, so exposed liquid water tends to freeze, boil away, or evaporate rapidly depending on the conditions. But Mars wasn't always like this. Billions of years ago, the planet had environments where liquid water flowed across its surface. Ancient valleys, lake deposits, deltas, and water-altered minerals show that Mars once had a much wetter past. NASA's Curiosity mission has also been finding evidence that ancient Gale Crater experienced environments potentially suitable for life as we know it. Then Mars changed. Its atmosphere became much thinner. The surface became colder and drier, and enormous amounts of water became trapped as ice or were lost from the planet's surface environment. But here's the important distinction. Scientists aren't saying every underground bright radar signal is automatically water ice. Radar has to be interpreted. Different materials can produce different echoes, and scientists compare the strength, shape, and continuity of those echoes with what physical models predict. That's where instruments such as SHARAD, aboard NASA's Mars Reconnaissance Orbiter, become incredibly useful. SHARAD sends radio waves into the Martian subsurface and records echoes from boundaries between materials. It operates between about 15 and 25 megahertz and can investigate the upper kilometer or so of the crust under favorable conditions. ESA's Mars Express carries a different radar instrument called MARSIS, designed to probe deeper. Together, these instruments have allowed scientists to see something that ordinary cameras can't: the hidden architecture of Mars. And once researchers started mapping that architecture, the planet's past began appearing in layers. Imagine flying over Mars and seeing nothing unusual. Just dusty plains, craters, wind-sculpted ridges. Now imagine turning on a radar. Suddenly the planet becomes transparent, not completely, but enough to reveal boundaries hundreds or even thousands of meters beneath your spacecraft. This is what makes radar so powerful. In Utopia Planitia, in Mars's northern mid-latitudes, SHARAD observations revealed a huge subsurface deposit rich in water ice. Researchers analyzed data from more than 600 radar passes and concluded that the deposit contains roughly as much water as Earth's Lake Superior. It covers an area larger than the U.S. state of New Mexico, and that wasn't an isolated discovery. SHARAD has also identified widespread glacial ice deposits in the Martian mid-latitudes, including deposits up to about 1 kilometer thick in Deuteronalis Mensae. In many places, rocky debris appears to have helped protect the buried ice from sublimating directly into the atmosphere. Then there are the polar regions. Radar has revealed enormous layered deposits beneath the north and south polar caps. At Mars's North Pole, The layered deposits contain alternating structures of ice and dust that preserve evidence of changing environmental conditions. NASA describes these layers as a record of past Martian climate changes. This is the moment the simple picture of Mars begins to crack. The ice isn't just a frozen resource. It's geological evidence. Every boundary, every layer, every change in composition may represent a different chapter in Mars's environmental history. But why would Mars repeatedly move water around its surface and atmosphere? To answer that, scientists had to look beyond the ice itself. They had to look at Mars's orbit. Mars doesn't simply travel around the sun like a perfectly steady clock. Its orbit changes. Its axial tilt changes. And those changes affect how sunlight is distributed across the planet. On Earth, long-term variations in orbital geometry are associated with Milankovitch cycles, which influence climate over tens of thousands to hundreds of thousands of years. Mars experiences its own orbital and axial variations, but they're much more pronounced. When the tilt of Mars changes significantly, the balance of sunlight between the poles and lower latitudes changes too. That can alter where water ice is stable. Scientists have used climate models together with geological and radar evidence to reconstruct periods when water ice migrated away from the poles toward lower latitudes. During a Martian ice age, water vapor can move through the atmosphere and accumulate as ice at lower latitudes. Later, as the climate shifts again, that ice can retreat toward the poles or become buried beneath dust and sediment. NASA research indicates that the most recent Martian ice age ended roughly 400,000 years ago, with the polar deposits subsequently gaining additional ice. So ask yourself, what would a climate record look like on a planet where the climate itself can move enormous amounts of water from one region to another? The answer may be frozen beneath our feet, if we ever get there. But scientists soon encountered an even bigger mystery. Some of the thickest deposits weren't near the poles. They were surprisingly close to the equator, and that discovery forced researchers to reconsider how much water Mars once moved around its surface. The Medusae Fossae Formation is one of the strangest regions on Mars. It stretches along part of the boundary between the planet's northern lowlands and southern highlands, and is heavily shaped by wind erosion. For years, scientists debated what these enormous deposits were made of. One possibility was volcanic ash or other fine-grained sediments. That explanation made sense because Mars has extensive volcanic deposits, and the Medusae Fossae Formation has unusual, wind-sculpted structures. But there was a problem. The deposits are extraordinarily thick. When Mars Express first studied them with Marsis more than 15 years ago, radar observations revealed deposits reaching roughly 2.5 kilometers deep, but scientists couldn't confidently determine their composition. Then the data improved. Researchers returned to the region with newer Marsis observations. The radar echoes showed internal reflectors and electrical properties that were difficult to explain with a simple stack of dry dust or volcanic ash. In 2024, a study published in Geophysical Research Letters concluded that the radar evidence is consistent with a layered, ice-rich deposit beneath an ice pore cover. The researchers estimated that the ice-rich component across the Medusae Fossae Formation could represent a global equivalent layer of roughly 1.5 to 2.7 meters of water, depending on the assumptions used. That's an enormous amount of water. But there's an important scientific caution. Radar doesn't produce a photograph of blue-white ice underground. Scientists infer composition from electromagnetic properties, layer geometry, radar reflections, and physical modeling. That distinction matters. Science isn't about taking the most exciting interpretation. It's about asking whether the evidence survives alternative explanations. And in this case, the evidence became much harder to dismiss. But then new data changed the scale of the story. Here's where it gets really interesting. The newer analysis showed that parts of the Medusae Fossae Formation could be up to about 3.7 kilometers thick, roughly the height of a mountain beneath the Martian surface. And the radar reflections resemble those seen from Mars' known ice-rich polar deposits. That's the twist. What looked from above like dry, wind-sculpted material may conceal an enormous layered body of ice. Imagine the surface as a lid. Underneath it is a frozen structure built over ancient environmental cycles. The dry cover is important too. Researchers estimate a cover of roughly 300 to 600 meters over the ice-rich component in the Medusae Fossae Formation. That cover could help shield buried ice from direct exposure to Mars's extremely dry atmosphere and slow its loss through sublimation. But here's the question that scientists still can't answer completely. When exactly did all this ice accumulate? And what was Mars like when it happened? The layers might encode changes in atmospheric conditions, orbital geometry, dust transport, and the movement of water. On Earth, scientists drill ice cores from Greenland and Antarctica and read trapped chemical signatures, dust layers, and atmospheric bubbles to reconstruct past climates. Mars doesn't give us that luxury yet. No human has drilled a kilometers-deep Martian ice core. No laboratory has yet received a pristine core from one of these buried deposits. So for now, orbital radar is doing the detective work. And it is revealing a planet that was far more dynamic than the dry world we see today. So how does radar actually tell us what's underground? Picture the spacecraft flying hundreds of kilometers above Mars. Marsis, or Charade, sends a pulse of radio energy toward the surface. Part of that signal reflects from the ground. Another part travels deeper. Whenever the signal encounters a boundary where the electrical properties change, some energy can reflect back toward the spacecraft. The instrument records the timing and strength of those echoes. Scientists then transform the measurements into radargrams, essentially cross-sectional views of the subsurface. A strong, continuous reflector can indicate a major boundary. Repeated internal reflectors can reveal layering. And the speed at which radio waves travel through material provides information about its electrical properties. Water ice has different electromagnetic behavior from loose dust or compact rock. That doesn't mean radar can identify every material with absolute certainty. But when the radar geometry, dielectric properties, layering, and known surface geology all point in the same direction, the case becomes much stronger. That's exactly why the Medusae Fossae findings are important. The 2024 research found that the observed subsurface structure is difficult to reproduce using homogeneous fine-grained material alone. The inferred electrical properties and internal layering fit better with a thick, ice-rich deposit beneath a drier cover. And polar radar provides a comparison. At Mars' North Pole, radar has revealed layered ice deposits whose structure records major changes in climate. Some layers correspond to changes in accumulation and erosion associated with past ice age conditions. So the ice beneath Mars isn't simply frozen water sitting there by accident. It is part of a planetary climate system, a system that moved water, buried it, exposed it, and buried it again. If you're beginning to see Mars less as a dead desert and more as a planet with a complicated climate history, hit like. Because the next question is even more important. What can we actually do with all that ice? If this story changed the way you see Mars, hit like. If you have a theory about what those buried layers could reveal, drop it in the comments. And follow the Coded Tales for more science stories, space discoveries, and mysteries hidden across our universe.